Good morning, everyone. Good morning, everyone. Welcome to the Mercury Virtual. Hope you are doing good. Today I'm going to take a session. Today I'm going to take a session on this. We can say this approach that is known as representing the information. In the last class we have finished. In the last class we have started with this schedule. That is how to do this one, how to make this one. So shall we begin the session? So let's start with chapter number 2, that is representing and manipulating the information. Okay. First part is representing and manipulating the information. How we can represent, how we can manipulate the information. That includes information storage, that includes integer representations, integer arithmetic, floating point, summary. So when we say that the representation that include the C++ programming languages that is built upon the C, upon the exact as same as it is used with the numeric value, it is used with the numeric value. So first part is the information storage. Part is the information storage, that is how the data will be stored. So first of all, it is stored in the bytes, virtual memory, virtual address. So it is stored in the bytes, it is stored in the bytes, that is the bytes is the smallest addressable units of a memory. So it uses the program object, it uses the RAM, that is random access memory, the storage, special hardware, operating system software to provide the program with what appears to be a monolithic byte array. So we store the different program object, that is the program data, instruction, and also controls the information. Various mechanisms are also used to allocate and manage the storage for different parts of a system, different parts of program, whatever the different part of a program that is managed, that is used for the storage, that is used for the different parts, that is used for the different content. For example, the value of a pointer in C, whether it points to an integer, structure, or some other program object, that is a virtual address of the first byte of some block of the storage. Then we use the C compiler that also associates the type information with each pointer so that we generate the machine level code with the value stored at the location designated by the pointer depending on the type of that value. And when we use the C compiler, that also maintains this type of information, that is an actual machine level program that generates no information about the data type. The next one is the hexadecimal notation. A single byte consists of 8 bits. In binary notation, its value ranges from 0000 to 11112. When viewed as a decimal integer, its value ranges from 010 to 25510. Neither notation is very convenient for describing, neither hexadecimal is used for describing. That uses the digits from 0 through 9 along with the characters A through F to represent the 16 possible values. And we are using the hexadecimal digits written in the hexadecimal values of a single byte that can range from 0016 to FF16. And it is used with the numeric constraint, it is used with the character that may be written as a F in either uppercase or the lowercase. For example, we could write the number, these are the number, or even mixing upper and the lower case. Example 0xFA1D37B. Then we use the C notation for representing hexadecimal values in this book, and the common task in working with the machine level program is to manually configure or manually convert decimal and the hexadecimal representation of the system with the binary digits with the usage that is available with this pattern or the bit pattern. And when we convert the binary and the hexadecimal is straightforward since it is performed one hexadecimal digit at a time, and can also be converted by referring to a chart that is available in figure 2.2. Now let's see what is the figure 2.2. This is hexadecimal digit 012347, decimal value 01234567. Binary, these are the binary representation, binary, hexadecimal digits 8, 9, A, B, C, D, E, F, decimal value 8, 9, 10, 11, 12, 14, 15, binary. This is the binary representation of these 18 numbers, values. Then hexadecimal notation, then next one is the binary notation. So one is used as a hexadecimal notation, one is used as a binary notation that will give the representation of the binary notation of the common value that is used with this one. Now these are the various practice problems that can perform the following number conversions. This is into binary, then binary into hexadecimal, then this into binary, binary into hexadecimal. So when the value x is a power of 2, that is x equals to 2 power n for some non-negative integer value, we readily write the x in the hexadecimal form by remembering that the binary representation of x is simply 1, that is followed by the n zeros. This is with the use of the decimal and the hexadecimal representation with the different powers of the 2. Now this is the practice exercise, practice problem 2.3. This is a decimal, this is a binary, this is the hexadecimal. Now converting between decimal and the hexadecimal for representing or for converting larger values between decimal and hexadecimal, it is best to let a computer or calculator to do the work. For example, when we use a script used in the Perl language, it converts a list of the numbers from decimal to the hexadecimal. And without converting the number to decimal or binary, this is used to solve the following arithmetic problem that is given in the answer in the hexadecimal. Then words. This computer has a word size indicating the normal size of the integer and pointer data, and since a virtual address is encoded by such a word, the most important system parameter determined by the word size is the maximum size of the virtual address space. This is used with the virtual address space that is used with the 4 gigabyte GB, that is just over the 4 into 10 power 9 bytes. And although this is the ample space, or there is ample space for most applications that is used with the pointer, that is used with the scientific database applications that requires a larger amount of the storage, and consequently high-end machines with the 64 bits word sizes are also becoming interesting common as storage device decreases. And with the hardware cost increase, there is also a bit power, or the bit word size is also increased with this one. Next is the data sizes. So computer and the compiler support the multiple data formats using different ways to encode the data. For example, when we say about the integer, float, as well as a different length, that is of the different sizes, this is the simple bytes. One is a char, int, float, double. This is a C declaration, 32 bit, 64 bit. This is a char, 1 bit, 1, short int, 2, 2. Int 44, long int 48. This is used with the C data types, and the exact number depends on both the machine and the compiler. We shall use sizes for the 32-bit, 64-bit machines, and we can use a short integer that having the 2-byte allocation, while an unqualified int that is for the 4 bytes. Now addressing and the byte ordering, how we can address and byte ordering, that is the big integer or the short integers. So when we represent the information, that is represented with the help of the assembler also, deassembler also, that is used by ordering, that becomes very important in looking the byte sequences that represent the integer and the data, and that occurs often when inspecting machine leveling instructions or the low level instruction. Now this is one of the example that shows a high-level program that includes stdi.h. This is a type def unsigned byte integer that also represents the unsigned char byte pointer. Then void show bytes, byte pointer start, int len I equals to 0, I is less than len, I plus plus, printf percentage to x, start I. So this is used with the start I, this is used with the len. Now next is void show int x, then show bytes, byte pointer x, size of int, then float, then show bytes, byte pointer, size of float, then show pointer, void pointer x, then show floats, byte pointer, size of void. Now this is the code that is used to print the byte representation of the program object. This code uses the casting to circumvent the type system, and the similar function are also easily defined, are also usually defined for other objects or other data types also. That includes a machine level language, that includes a machine codes for the different data for different scenario. And the third case where the byte ordering is very important is in the use of the C language, C++ or the programming language. Now next is the pointers and the arrays. Whatever the pointer, whatever the array we are using, that is used with the C language. So there's a need to be formatted with the printf. There's a printf statement that is used. That is used with the fprintf, sprintf. That provides a way to print the information with considerable control over the formatting details, whatever the formatting details we are using. And the first argument is the format string, while remaining arguments are the values to be printed. And within the format string, each character sequence start with the percentage indicates how to format with the next argument, and typically includes percentage %d to print a decimal integer, f to print a floating point number, and c to print a character having the character code given by the argument. Then pointers and the array, this is used to represent the unsigned char, signed char. This is used with the start I, with the pointer, with the procedure that is used with the show int, show float, and the show pointer that demonstrate how to use the procedure show byte to reprint the byte representation of the C program array with the floating point with the integer. Next is the Linux 32, Windows, Sun, Linux 64. And one argument, that is 12345, has a hexadecimal representation with the 0x0003039. For the in data, we use identical results for all the machine except the byte ordering that is used with the byte ordering that is used with the pointer value that are completely different. And the different machine operating system configuration is also used with the test data, test byte, show byte that is used with the ival that is equals to val, then fval that is equals to float val, then pval equals to ival. Then next is byte representation of the different data values that results for the int and float that are identical except for the byte ordering, and the pointer values are also machine dependent that is used with the floating point number, that is used with the integer number, that is used with the hexadecimal pattern in a binary format. Now next is using the show int and the show float that determined with the integer has a hexadecimal representation with the floating point numbers. The next is representing the strings that is used with the ASCII, American Standard Code for the Information Interchange, that is used with terminating the byte as a hexadecimal representation. Then representing the codes, and when compiled with the simple machines, we generate the machine code having the byte or the following byte representation, following byte availability that is used with the Sun, Windows, Linux, whatever the system that we are using. Now next is the Boolean Algebra that is used with the bit, that is used with the byte. Now the Boolean includes a true and the false. One is a true value, one is a false value. True value is represented with the 1 and the false value is represented with the 0. So he could formulate an algebra that captures the basic principle of the logic reasoning that is used with the defined values 0 and 1. The defines for various operations in the algebra, and R symbol for representing will be discussed later, and the Boolean operation is also corresponding to the logical operation node that are denoted by this one. That is to say, note of P is true when P is not true and vice versa. Correspondingly, note of P equals 1 and P equals 0 and vice versa. This is P and Q that holds when the P is true and the Q is also true. That corresponds P and Q equals 1, only when P equals 2 and Q equals 2. And we can also extend the 4 Boolean operations to also operate on the bit vectors that is used with the zeros and ones of the same fixed length W. And we define the operations over the bit vectors according to their applications to the machine or the matching element of the argument. Let A and B are the defined vectors that is used. So we use a bit vector of the length W where the ith element equals AI, BI. Now this is the table that's showing the result of the evaluating Boolean operations on the bit vector. This is operation, this is the result. This is A, B, notation of A, notation of B. This is A and B, A or B, and the A not B. Now this is a Boolean ring that is available with the AND, NOT, OR. This is used with the finite operation. Then red, green, and blue. These are the various colors with the bit level operations in C. These are the bit level operations. Then these are the problem. Now next is the logical operators, that is OR, AND, or NOT.